Hey, this is Horner, and this is Waves and Sound. Free response question number 2. A student wants to find the speed of sound as air travels through the classroom. Luckily for you, we have done this lab, which is really, really nice. They want a procedure where you would use this tube with water in it, another tube, and a tuning fork. So this guy up here, that's supposed to be a tuning fork. And they want to tell us what we need to do in order to measure everything. So here we've got a movable tube, we've got the tuning fork on top and the graduated cylinder. And the 4 steps that you want to do here is you want to say you hold the tuning fork over the movable tube that is in the water, adjust the tube until you hear, so move the tube up and down until you hear resonance or you hear the loudest sound. And then measure the length of the tube above the water. And the one thing I forgot here is you probably want to write with the meter stick, because you need to use common materials is what they ask you to do. Then to minimize error, because they always want you to include something that would reduce experimental error, is to do 3 trials with different tuning forks. And that would be a great procedure. Explain how the measurements could be used to find the speed of sound. So since the closed tube is 1/4 of a wavelength, the length of the tube is 1/4 of a wavelength. One wavelength is 4 times the length of the tube. In order to get the graph so that we can find the speed of sound, we have to graph the wavelength versus 1 over frequency, and here's why. If you were to just graph wavelength times frequency, you're going to get a hyperbolic curve. Why is that? Because remember, wavelength times frequency, when they're next to each other, when frequency goes up, wavelength has to go down for the same speed of sound. So what I have to plot is V will be our slope, and so we really want to plot the wavelength versus 1 over frequency. So if I plot wavelength and then 1 over frequency, okay, like we see here, then our equation is wavelength is equal to speed over the frequency, and that gives us wavelength is equal to the slope times 1 over frequency, and that's where that straight line would come in. If you try to plot it this way, you're going to get this, and then you have to explain that you have to linearize it. So this is 1, 2, 3, 4, 5, 6 points so far. This is a 12-point problem. In the next part, it wants us to outline a procedure where we can make measurements to determine the speed of sound in air using 2 speakers. So I need to demonstrate for this to you in class so that you can actually see how this happens. It's really cool. So we will do this, but you'll have to remind me. You place the 2 speakers 1 meter apart. You stand 3 meters away. And then what we'll do is we will move the speaker until the sound gets really soft. And then we'll move it again until it gets loud. And we're going to measure those. And that's basically what you see here. Then you'll do it again. You'll put the speakers back. We'll find a new frequency. So we'll change the frequency, and then we'll move it until it gets soft and then gets loud again. You'll see that the positions are a little bit different. From the soft to the loud distance is actually 1/2 wavelength. So from here to here, this is 1/2 of a wavelength. From loud to loud, this distance is going to be 1 wavelength. You can find that wavelength either way, so you just have to describe it. And then once again, we have to plot wavelength versus 1 over frequency, and the slope would be the speed of sound. So I really like this question. I'm hoping there's something on the test like this year. If so, you'll rock it. That's 12 points, believe it or not, and it took half the time as the last problem.